Right, so this unit of work we're going to be looking at something called partial fractions. Now partial fractions are a reverse operation to dealing with fractions in a way we're far more familiar with, which is to combine them. As we'll see in this example, this is work we were looking at in the previous piece of work on algebraic fractions. If we wanted to write that as a single fraction, then we would combine the two denominators because they're independent factors. So we would write the denominator like that, and then to work out what goes on top, if we divide this into that combined denominator, it leaves us x plus 4. So the equivalent top would be 2x plus 4. And then if we divide that denominator in, it goes in x plus 5 times. So we'd have plus 3 bracket x plus 5 like so. We then expand and simplify the top of that. So we get 2x plus 8 plus 3x plus 15. We would leave the denominator as a product of two factors. The top of that simplifies to 5x plus 23 over x plus 5x plus 4. So that's a skill that we've already got, the ability to combine fractions like that. However, there are instances in A-level maths where it is more desirable and easier to work with the sum or difference of two or three or more simple fractions than to deal with something like that. And certainly when we come to looking at integration further on down the line, we will see how this process helps us. So, partial fractions is the reverse process where we take a fraction like that and break it into the sum or combination of its simpler parts. Now, in order to do that, there are a number of recognitions that you have to make in order to be able to set up the correct form of our partial fraction. And the way that we do that, we need to look at how the denominator, or the algebra in the denominator, looks. There's three different things we need to spot, and we'll break those down by increasing complexity. The first type is if the denominator consists of linear factors. So by linear factors, I mean that each factor has got an order no greater than 1. So you haven't got any x squareds or x cubes or anything in there that you can't factorize further. So if that is the case, then there is a specific way that we start these partial fractions. So we'll take a look now at these two examples. So the first example is 5x plus 1 over x minus 1 x plus 2. So we can see that I've got a pair of linear factors. Now for each one of those, the numerator is going to be a constant. So for this one, we're going to have some constant a, and then for the x plus 2, we would have a different constant x plus 2. And that's the spot that you have to make. Linear factors, so it's a over one of the linear factors plus b over the other. What we then do is we combine that as if we were to be building a single combined fraction again. So if we were to do that, so these should be equivalences. because they're true for any value of x on either side. What we would have on this side is the same denominator, and then it would be that divides into that, leaving x plus 2. So we'd have a x plus 2 plus b, and then that would divide in, leaving x minus 1. So because these fractions have to be equivalent, because what we want to work out is what values of a and b make them so, the denominators are the same, which means the numerators must be the same as well. So if we consider the numerators, that 5x plus 1 has to be equivalent to ax plus 2 plus bx minus 1. Now there are two methods that we can use to find the values of a and b. One of the methods is pretty reliable when we're working with linear factors in the way we are here, but the method breaks down with more complicated equivalences that we're going to be moving on to. But I'll show you both methods, the method that works for all of them and the sort of shortcut method, and it's up to you what way you go. So if we look at method 1, so method 1, what we want to do first of all is choose a value of x which will make one of these constants become 0. So if we choose x as 1, then b is going to be b times 0 is 0. So if we let x equal 1, the left hand side would be 5 times 1 plus 1, and that's going to equal, and we're going to put an equal sign rather than equivalence there now because we're putting specific values into it. So that will be equal to a 1 plus 2 plus b lots of 0. I've written that line in its complete form. You can shortcut that as much as you like. So you can see there we have 6 equals 3a. So a is 6 divided by 3, 2. So we've worked out that the constant a has the value 2. So that's made that go to 0. Now we find the value of x which will make this one go to 0. So if we let x equal negative 2, that would be 0. So the left hand side then becomes 5 lots of negative 2 plus 1 equals 0 lots of a plus b negative 2 take 1. So we got minus 10 plus 1 negative 9 equals minus 3b. So b is minus 9 over minus 3. Minus divided by minus is a plus. 9 divided by 3 is 3. So that gives me my a value of 2, my b value of 3. The alternative method, which in this instance probably is a bit more labour intensive, but works for all the partial fractions that we're going to be looking at, so it depends how comfortable you are learning multiple methods. What we do for method 2 is we compare the coefficients. So I'll just go back to this line here and expand this out. So multiplying that, I get ax plus 2a. Multiplying this, I'm going to get bx minus b. So if those are to be equivalent, then the x terms on this side have to be the same as the x terms on this side. So that 5 has to equal whatever the ax and the bx add up to. So this is where we say compare coefficients. So in this instance we've got x coefficients, which are x to the power of 1. So we have a plus b is 5. Equation 1. And then the numerical ones, so x to the power of 0, anything to the power of 0 is 1. I'm going to have 2a minus b equals 1. So I have a pair of simultaneous equations to solve. Easy in this instance, I can add 1 and 2 together, and I get 3a is 6, giving me a is 2, which is the same as I got from the previous method. And then if I put that into 1, I get 2 plus b equals 5, leading to b as 3. So 2 methods doing the same thing. This method we will use extensively as the examples get more complicated, but with this first type of partial fraction, the inspection way works just as well. So just to finish it off there, we can say that therefore the fraction 5x plus 1 over x minus 1 x plus 2 is equivalent to a 2 over x minus 1 plus b 3 over x plus 2. So in previous algebraic work we will have taken that and produced that. We've now got a skill that enables us to go in the opposite direction. So that's the first example. Let's take a look at the second. So EG2 express 4x minus 2 over x cubed minus x as a sum of its partial fractions. Now, if we go back to the previous example, I said that we were looking at linear factors, and when we had linear factors, then there would be a constant over each individual linear factor. Looking at this example as it stands, we don't have a linear factor. We've got a cubic expression there. But there are cases where we can simplify that by factorizing the denominator. And I can see here straight away I can take x out as a common factor. Leaving me x squared minus 1. In that form, it's still not a pair of linear factors because that's got a quadratic term. However, I'm spotting difference of 2 squares, which means that I could go on and write that as x bracket and then x plus 1, x minus 1. And there now are my string of linear factors. So 4x minus 2 over x bracket x plus 1 x minus 1. When I break this up, I'm going to have a constant over each of those linear factors. So a constant over x, a constant over x plus 1, and a constant over x minus 1. I then combine the fractions in order to work out what the equivalent numerator is going to be. So we're just going to deal with the numerator. When I divide x into that, it leaves me x plus 1, x minus 1. So it'll be a x plus 1 x minus 1. When I divide the b factor in, it's going to take out the x plus 1, leaving me x minus 1. And when I divide the c in, it'll take out the x minus 1, leaving me x bracket x plus 1. Okay, so if we go for method 1, in order to make the x minus 1 go to 0, I'm going to put x as 1 in. So if I put x equals 1, on the left hand side I'm going to have 4 minus 2, which is 2. And on the right hand side I'm going to have 0 in that one, 0 in that one, and in this one I'm going to have 2c, which means c is 1. If I put x as minus 1 in, then on this side I'm going to end up with minus 6. On this side I'm going to end up with a 0 in here. I'm going to have a 0 in there, and for b I'm going to end up with b times minus 1 times minus 2. Minus 6 equals 2b. Negative 1 times negative 2 is positive 2. So b will be negative 3. So I've worked out my c and I've worked out my b. And then to find a, if I put in the constants I already know now, so this becomes 4x minus 2 equals a x plus 1 x minus 1, b is minus 3, and c is 1. So I've only got one constant in there now, so all I have to do is choose a different value of x. So if I choose x to be 2, then my left hand side will be 8, 6. This will be a 3 times 1. This will be 3, 2 times 1, and this will be 2 times 3. So 6 is 3a minus 6 plus 6. So they will cancel. 6 is 3a, a is 2. So that's how I've worked out my a, b and c using method 1. Going to method 2 as an alternative. So I have 4x minus 2 is equivalent to, so I'm going to expand these brackets now, a x squared plus x minus x is 0x minus 1. For the second one, plus b x squared minus x plus c x squared plus x. So I need to compare my coefficients. So this time I've got x squared terms. I've got an ax squared and a bx squared and a cx squared. So a plus b plus c. But on this side there is no x squared, so they have to give me 0. Then my x terms, I've got no ax term, I've got a bx minus b plus c equals 4. And my number only terms, x to the power of 0, I have minus a, nothing there, equals minus 2. So a from that is 2. And then from 2 I can rearrange that to give me b is c minus 4, making the b positive, bringing that over. So if I sub then into equation 1 for a and b, instead of a I can write 2, instead of b I can write c minus 4 plus c equals 0. So simplifying that, I've got 2c minus 2 equals 0. So 2c is 2, c is 1. And then if I put that into equation 4, b is c minus 4, making negative 3. So whichever way you choose to do it, you're going to end up with c is 1, b is minus 3, a is 2. So to finish it off, we can therefore write our equivalence. So 4x minus 2 over x cubed minus x, which is the form we were given, is the same as, it's equivalent to a over x, so 2 over x, b over x plus 1, b is minus 3, plus c over x minus 1, and c is 1. So again, previous skill would be to take that and turn it into that. We're now able to go the other way as well. So if we look back at our notes, we've done example 1. In some cases it's necessary to factorize the denominator. We did that for example 2. And as example 2 demonstrates, the denominator can contain more than 2 linear factors. And that's why we ended up with an A, a B and a C, and if necessary a D and an E, and so on and so forth. But as far as exams are concerned, at most you will get those 3. And then the final note to point out is that when you're working with partial fractions, it's important to check before you start that you are dealing with proper fractions. By proper fractions, it would be where the order of the numerator is smaller than the numerator of the order of the denominator. So in number terms, it's not top heavy. So 3/4 is a proper fraction because the number on the numerator is smaller than that on the denominator. It's the same with algebra. So if we take a look at this one here, first of all, the order of the numerator is order 1, because we've got x to the power of 1. The order of the denominator is 2, because the largest power of x is 2. The order of that is less than that, so that is a proper fraction, and one that we can deal with using partial fractions. So order 1, order 2, proper. With this one, the highest order on top is 2, on the bottom is 2. They have to be, that has to be bigger than it, is equal to it, so that is improper, top heavy. So that one is improper. And this one, order 3 over order 1, also improper. So you're looking for your fractions to make sure that they are proper. If you look at above, that one's order 1, that would expand to give a quadratic, so that's fine. This one, order 1, order 3, they're fine. Now, I wouldn't expect you in an exam to have to spot that. It's likely that if they're asking you to do a partial fraction, it'll be in that format anyway. If you end up with versions like this, and I'm not going to go through the whole process because I don't think it's necessary, what you would then do is, just like if you had 7 quarters, to turn it into a mixed number, you would say, you would divide the 4 into the 7, it goes once, with a remainder of 3 quarters. So you would then work with that as a partial fraction. Same thing you would do here. For this one, you would have to do the long division, which you would have learned how to do when you're doing factor theorem and remainder theorem, and divide it into 3x squared plus 2x plus 6. What you end up with here is mixed number part, the 1, and then you would write the remainder over the denominator to get the fraction part. And you would do the same with this one. You would have to divide 5x minus 3 into 2x cubed plus 3x squared minus 7 and go from there.